Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on January 22nd, 2026, just yesterday. It introduces a new native computer use agent called EvoCUA that achieves a success rate of 56.7% on the OS World benchmark, surpassing leading closed models like UI-TARS 2. The paper is titled EvoCUA, Evolving Computer Use Agents via Learning from Scalable Synthetic Experience. And as we'll see later, the shift from static datasets to evolving experience scaling is what makes this approach so effective. And for those interested in the implementation, the authors have shared their code on GitHub. On Hugging Face, both the 8 billion and 32 billion parameter models are available. Check out the examples for automating apps using screenshots and natural language instructions. Figure 1 visualizes these gains on the OS World verified benchmark, where the yellow bars highlight the new models. The EvoCUA 32B model reaches 56.7% success, which is a significant jump over the previous open source leader, OpenCUA 72B, shown here at 45%. It also outperforms the closed UI-TARS 2 model, which scores 53.1%. Remarkably, even the smaller 8 billion parameter version beats that 72 billion baseline, demonstrating the efficiency of this approach. So how does this system achieve these results? Figure 2 provides an overview of the pipeline, which replaces static imitation with a continuous learning cycle. It starts in the top left with the verifiable synthesis engine, creating tasks paired with executable code to strictly validate success. These flow into the scalable interaction infrastructure on the right, where tens of thousands of concurrent sandboxes generate massive interaction data. Finally, the iterative optimization module at the bottom uses this experience to refine the policy, climbing from basic priors to advanced reinforcement learning. Well, Figure 3 zooms in on that verifiable synthesis engine to show how it actually creates training data. On the left, the process begins with structured task space construction, which combines a hierarchy of tasks with real-world files, like spreadsheets and slides to ensure diversity. The core innovation sits in the middle panel, the agentic dual-stream synthesis. Here, a task architect model generates both a user instruction and a code-based validator at the same time, ensuring every task has a clear success metric. Finally, the right panel shows the rigorous quality assurance stage, which filters out low-quality outputs to produce the final verifiable dataset. Now that we have tasks, Figure 4 lays out the engine that runs them, the scalable interaction infrastructure. It starts in the top left, where the online reinforcement learning loop generates massive streams of interaction requests. These flow into the high-throughput orchestration layer, on the right, which uses an asynchronous gateway and a distributed scheduler to manage extreme loads, supporting burst scaling of over 10,000 instances in under a minute. Finally, the bottom section reveals the actual execution environments, specifically the computer use sandbox, which uses QEMUK versus M virtualization and a patched operating system to ensure every interaction is stable and reproducible. So with the infrastructure generating data, Figure 5 illustrates the learning strategy, a dual paradigm direct preference optimization approach. The process centers on the critical forking point, which marks the exact moment the agent deviates from success. Paradigm 1, in the middle, teaches the model to simply choose the correct action over the error. The Paradigm 2 on the right is crucial for recovery. It trains the agent to pause and reflect, observing and planning, instead of blindly continuing, which optimizes the loss function on the far right. Having explored the learning methodology, Table 1 details the final performance on the OS World Verified benchmark. The table separates closed weights models at the top from the open weights models below. The most critical result sits in the bottom row, where EvoCUA 32B achieves a 56.7% success rate. This is particularly impressive because, despite using a stricter 50-step limit, it outperforms the previous open source state-of-the-art, OpenCUA 72B, which reached only 45% with 100 steps. It even surpasses the closed UI-TARS 2 model, highlighting how effective the evolutionary training is at producing capable agents. Wrapping up, two main points stand out. Moving from static datasets to scalable, interactive experience is a game changer for agentic AI. This work proves that with a robust synthetic training loop, smaller open source models can effectively outperform much larger competitors. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.